Hello and welcome. In chapter 4, we will be discussing about the standard single-purpose processors from the point of view of peripherals. Now, peripherals are the important components that work with the single-purpose processors to enhance their capabilities and offer them additional functionality. So, these single-purpose processors would become more functional and more powerful with the connection and integration of these peripherals with them. So basically, let's have a review of single purpose processors. We discussed before that single purpose processor, they perform a specified computing task, right? So they are designed for a specified computation task. And what are custom single purpose processors? They are designed by us for a unique task. So we are the designers of custom single purpose processors. Why do we design them? Because they are not available, so we designed our own processor. On the other hand, we also have the standard single purpose processors, and as we discussed before, standard single purpose processors are off the shelf processors, as they were pre-designed for a common task by the designers. So we just take those standard single purpose processors and we can use in our project. The term that is used, IP or intellectual property, right? So when we talk about intellectual property, we can have the peripherals and we can obtain the peripherals as intellectual property and we can use them. And we should also know that IP can be purchased both as software or as coding. For example, coding in VHDL, Verilog, or System C for that matter, or the standard single purpose processors can be purchased as hardware components, as silicon wafers that have already been built, and the electrical connectivity can be made with those IC chips of those peripherals with our single purpose processors by a process that is called stamping. So basically, when you have a hardware version of a peripheral, you can directly use it with your hardware IC of a single purpose processor by using the process of stamping. So some common single purpose processors include serial transmission, peripherals include serial transmission, analog to digital converters, and so on and so forth. So this chapter is dedicated to these kinds of peripherals that are there. There is an excellent website that's called opencodes.org. I would invite you to visit that website. That website contains source code in the hardware description languages for different kinds of peripherals and codes that can be used. So the coding for these peripherals are usually called cores. So you can find codes for different kinds of hardware components, for example serial transmission and so on. So if your original single purpose processor is also in the form of an IP, basically in the form of coding of any sort, so you can use any core from this website and you can integrate with your IP, and that would be more analogous to writing code, because you would be interfacing two codes, the codes for your IP in hardware description language and the code for your particular open codes IP that you have had. So we start with the most important peripherals. I would say that no embedded system is complete without these peripherals. So these are called timers and counters. Timers, counters, and a special class of timers that is called as the watchdog timer. So what is the function of the timer? Timer measures time intervals, right? And the timer measures time intervals, and what is the use of this measuring time intervals? To generate timed output events. So for example, if we want to hold the traffic light green for 10 seconds, we start a timer. The timer, we would turn the green light on and would start our timer to count, and the timer will count for 10 seconds. After that, we'll turn off the green light. And timers can also be used to measure input events. For example, we can measure a car's speed. right? So how we can measure the card speed? For example, we can have a sensor over here, and we can have a reflector, for example, over here. It might be a laser gun and it might be a reflector over here. So it can count the number of reflections. When this reflecting surface is close to the laser gun, all the light that is shown on it is reflected onto the receiver, right? So we can find RPM using input events. So this would be an input event. This would be high when this reflecting surface is near the reception end, and so on. So we can count the RPMs, and we can use the RPM to find the card speed. And of course they are based on counting clock pulses. So what is the basic function? We are counting the clock pulses. So for example, if you have a basic timer over here, which is a 16-bit up counter, so what is the maximum value? The total number of values can be 2 raised to power 16 minus 1 as per the rules of binary, right? This is basic knowledge. So this is an oscillator which is generating pulses. So the output of this oscillator, which is a sequence of pulses, would be input to the clock input of this timer, and it would count basically the number of pulses. And if we want to reset this count to 0, we can have the reset signal. There is also a top signal that becomes 1 when the counter overflows. So we can keep track of this to keep track of the number of times the timer has overflowed. So for example, let this clock period is 10 nanoseconds, and if we count 20,000 clock pulses, so how much time has passed? 200,000 into 10 nanoseconds, right? So sorry, 20,000 into 10 nanoseconds, or a total of 200,000 nanoseconds, and we divide it by 1 raised to power 6 to get 200 microseconds. So 200 microseconds have passed. So we can keep track of time. And what would be the maximum value that the 16-bit counter could count? The 16-bit counter could count, which this is the maximum number of that can be stored in the 16-bit counter, which is this, which is what? It is 2 raised to power 16 minus 1, or 65,536 minus 1, which is 65,535. And what is the resolution? This 10 nanoseconds is called as the resolution of this timer. So we multiply the maximum value with the resolution to get 655,350, right? And if we divide by 10 raised to power 6, we get 655.35 microseconds. So this 655.35 microsecond is called as the range of this timer, and this 10 nanosecond is called as the resolution of the timer. So range is this and resolution is this. Now let's look at some important things that we can do, right? If we increase the frequency, right, the time period would decrease, right? So if we increase the frequency, time period would decrease, and since time period would decrease, the range would decrease. Similarly, if we decrease the frequency, the time period would increase, so the range of the counter would increase, right? So what do we get by this? If we increase the frequency, the time period decreases or resolution decreases. So resolution decreases as a result of increasing frequency, but range increases. Okay, so this is the idea. So we can summarize that if we increase the frequency, resolution increases. Resolution increases. In other words, it becomes less, right? But range decreases. But if we decrease the frequency, resolution decreases. but range increases. That is the whole idea. Okay. So as we know this now, this bottom line becomes very important to us, right? How it becomes important? If we want to count large number of large time intervals, right? So we need to have a large range, yes or no? So if we want to have a large range, we usually make the frequency less, or in other words, we divide the frequency, and the component that is used for dividing the frequency is called as a prescaler. So the prescaler block is placed after the oscillator block, and the prescaler can divide the oscillator frequency, right? So it can be something like this. Let me draw whatever space is left. This is the oscillator block, and output of this oscillator is fed into the prescaler. Prescaler, right? So for example, if our frequency was 2 megahertz, for example, if it was 2 megahertz to begin with, and we have a prescaler of 2, so we are dividing this frequency by 2, so the output would be 1 megahertz frequency. That is basically the whole idea. Now let's look at counters. Counter basically is like a timer, but counts pulses on a general input signal rather than clock. The idea is, if our counter is not counting the clock or the output of the oscillator, but the counter is counting an external signal or an external element, then it would be termed as a counter. So for example, what are the examples of a counter? Count cars passing over a sensor, right? So we can often configure a device as either a timer or a counter. So in modern embedded systems, these are present as configurable devices. And what do we mean by that? The meaning is basically shown on this figure, right? So we have a 16-bit up counter with the reset signal, and this is the input clock of this counter. Now this input clock can be selected either as a clock. So if we select the clock as a source for this 16-bit counter, we are having a timer, because it is counting the number of pulses now, clock pulses. But if we configure the mux to select this count in signal, then as an input clock for this 16-bit up counter, so we are configuring it as a counter. So it is general purpose. We can have a timer or we can have a counter.